Again, everyone, this is Tom Sheehan in Boston, and I want to welcome you to the first webinar in our series that's sponsored by the project known as Sustainable Adaptive Gradients in the Coastal Environment, or SAGE program. This is a project that is funded by the National Science Foundation. It's a research collaboration network for science, engineering, and education for sustainability. And today I'm really pleased to welcome Dr. Scott Doney of Woods Hole about climate change and adaptation solutions for coastal ocean along the U.S. Northeast coast. Is a graduate of MIT, where he received his PhD in the MIT Woods Hole Oceanographic Institution Joint Program in Oceanography. And he was then a postdoctoral fellow and later a scientist at the National Center for Atmospheric Research before returning to Woods Hole in 2002. What I'd like to do is ask that any questions that people have, they can ask by typing in under the Q&A function. You'll see a Q&A tab at the top of the interface for WebEx. Please type your question in, and then at the end, we'll be reading these questions to Scott and ask him to address those questions. And I'm going to go ahead and turn it over to Scott and let him begin his talk for today. Scott?
So I'm going to talk today about some of the broad picture on climate change and how it's affecting the coastal ocean. And we're going to tap into, we have a new project here at Woods Hole that's been funded by the MacArthur Foundation, looking specifically at the sort of southeast England region, and I'll draw some lessons that we're already learning from that. And I listed on here a number of my collaborators on that project. Still gets to the webinar system. Part of the material I'm going to be discussing was drawn from the recent National Climate Assessment. An excellent resource, basic science of climate change, the observed patterns of change we're seeing across the country, but also impacts on different regions and different sectors of the economy. For example, there are specific chapters on oceans, on coasts, on the Northeast region, but also things like the energy cycle, the water system, agriculture, urban built environments, the transportation system. Everything's available online, and I would highly recommend this as an excellent resource that could then lead you deeper down into the scientific information that's available. So I touch on three different aspects of climate change that we're seeing in the Northeast region. Ocean warming, extreme events, storms and precipitation patterns, and sea level rise and coastal flooding. And I hope you'll see that these are often interconnected. They're not three independent topics, but they're linked in a variety of ways. So I'll start off talking about warming. This is a figure that many of you may have seen in various forms. The blue line is showing the increase in atmospheric carbon dioxide. Carbon dioxide is a heat-trapping gas that's released during fossil fuel burning and also during aspects of agriculture and deforestation. It has grown by more than 40% since pre-industrial levels, and it's the leading, though not always the only factor in driving human-driven climate change. Over 100 to 150 years, as atmospheric carbon dioxide has gone up, the blue and the red are shown the anomalies for the global temperature, where the 1800s, late 1800s, early part of the 20th century was a cool period. You saw warming around World War II, then a relatively flat period for several decades, and then beginning in the late 1970s, early 1980s, there is a rapid increase in temperature and warming on the globe. You'll note here that there's also substantial decadal variability. The human-driven climate change primarily due to carbon dioxide and other related greenhouse gases, such as methane and nitrous oxide and halocarbons. Is not, of course, the only game in town. There's a substantial amount of natural variability within the climate system and other external perturbations. But overall, looking at the entire record of observations, it is difficult to explain this rapid warming from over the 20th century and early 21st century with incorporating greenhouse gases as a dominant factor in that trend. You will people talk about a climate hiatus, so that the climate warming has stopped. And if you do look carefully at the decade or so, you will see that the climate warming is not as rapid over that period. The interplay between natural climate variability and this long-term natural trend, we can find other periods of a decade or so in the past record. We've seen either very rapid warming or very stable conditions. And really, when we're talking about climate change, we really have to put it in the context of long-term records, not focus exclusively on year or even multi-year, really short periods because of the interplay of the natural variability in the long-term trends. And that we're seeing in the United States, that's from observations over the last several decades, substantial warming over both the west and the northern parts of the country, as well as very substantial warming in Alaska. In New England, we're warming that's comparable to or larger than the global mean. And you look down in the bottom left-hand panel, you'll see the warming we're seeing across the U.S. region has a similar temporal pattern that we're seeing across the globe, where we are a relatively warm period during the very middle of the 20th century, a little bit of cooling through the 60s and 70s, and increasing warming over time since then. In terms of into the future, projection really requires us to look at multiple factors. Since a lot of the climate warming is associated with heat-trapping gases such as carbon dioxide that have long time scales in the atmosphere, really dates to hundreds of years in the case of carbon dioxide, very heavily on and future emissions of carbon dioxide and other heat-trapping gases. So when we're trying to think about what the climate might be in the middle or latter half of the 21st century, we really need to come up with estimates of what will be human behavior in terms of emissions, economic policies, technological developments, population growth. And done within the climate community is to build of representative scenarios that show a wide range of human emissions patterns. So in the upper left in this panel is shown some of the standard emission patterns that are commonly used to run climate simulations. The red solid line and dashed line are what I might call high emissions or business as usual scenarios. The dark green at the bottom is very low emission scenario where carbon dioxide emissions are basically reduced to zero or slightly negative before the end of the century. And it's not U.S. emissions, this is global emissions. Right now, we're close to the high emissions trajectory, and further action at the global level, it's likely that we would be in some of the lower emission areas that you see. Also see on that plot is the observational record. That's the black squiggly line. That's up to about 2012. And globally, we've seen a little over a degree and a half Fahrenheit warming over the annual cycle. And what's projected over the 21st century is anywhere from an additional 2 to 6 degrees Fahrenheit in warming. So the panels on the right are showing the projections for two of those scenarios. The top is sort of a middle emission scenario. The bottom is a high scenario, both of which show substantial across the entire U.S., given our current understanding of the climate system. And focusing in more narrowly on the coastal ocean, we are substantial warming already on the New England region. This is data in the upper left panel. It's for the northeast ecosystem, which stretches from basically Chesapeake Bay up in the Gulf of Maine, and the pattern of coastal ocean temperatures. So these are now water temperatures. You're relatively cool, similar to the patterns that we saw for the global temperatures, relatively cool at the start of the 20th century, warm middle part of the 20th century, a cool period, and then a recent very sharp warming period. In fact, in 2011 and 2012, we saw the warmest temperatures on record go for 150 years in these shelf ecosystems. And the bottom right panel is showing the distribution of that warming. We're warming both warming right along the coast and also offshore associated with shifts in the Gulf Stream. Now, about greenhouse gases warming, but the warming is very strongly patterned by in the atmosphere as well. In particular, that recent warming event we saw off the U.S. Northeast was in large part to changes in atmospheric circulation that we may be linked to atmospheric CO2. And during a typical winter, the Northeast experiences a number of air events where the stream dips south, comes out of the Canadian Arctic, and that not only cools the land surface, but also acts to cool the ocean surface very dramatically. During a recent warming event in 2011-2012, the Gulf Stream did not, or the jet stream in the atmosphere did not dip southward, and that was a large factor in that warming. So simply global patterns is we need to also understand regional patterns of change, which are associated with not warming directly of the atmosphere, but also changes in atmospheric circulation. One of the involved with the MacArthur Project is working with commercial fishermen to expand our observational system for coastal ocean. We have a lot of data, growing data set for the global ocean offshore the shelf. I have nearshore coastal measurements, many shelf regions. We have sufficient observational capability to track these warming events, which can have profound impacts, for example, on marine life and coastal fisheries. With the Commercial Research Foundation, actually put instruments onto commercial fishing boats. We had our training a couple of weeks ago, and we're already deploying instruments here south of New England, where we're making routine measurements commercial fishing. Not only do they allow us to expand our scientific capabilities, but this starts to engage them in making measurements that are very important for their livelihood and will enhance their ability to steward the marine resources that they depend upon. Projecting forward, I showed earlier the map, the model projections for the surface land temperatures. From coastal problems, we're interested in changes on a very local scale. I like to tell people that climate change, while a global phenomenon, will really only affect people or industry or cities, communities on the local and regional scale. And from the global climate models, which don't necessarily do a good job of representing that small-scale variability that you might need as a planner or a manager, whether for a community or for marine resources. That's a challenging problem. There are a variety of ways that people have gone about this. I'm just showing here results this is off the U.S. West Coast. That's Vancouver Island and Seattle and Puget Sound in very different, in one particular Earth system. Well, the left-hand panel is sort of the typical resolution that's being done for models, way too coarse to make significant management decisions. Right is a high-resolution run nested within a coarser resolution global model. One way to move forward. There are also statistical approaches that have been proposed for downscaling, and as computers become more advanced, actually running high-resolution models everywhere. The community still has a lot of skepticism about the ability of these downscaling methods at the point, but we're hoping to make progress in the near term. So, for a moment, I've been talking about temperature, but temperature is only one of a wide range of changes that I like to see in a changing climate. And in fact, I'm showing here 10 different indicators of a warm world, and there's strong observational evidence for all of these indicators showing substantial change. So I've talked a lot about temperature of the surface ocean. The ocean as a whole is also warming, so the ocean heat content reflects warming not just of the surface layer, but down at least the first 3,000 feet or so of the water column. We have good evidence of warming, and even warming in some deeper water areas. As waters expand, they actually, as waters warm, it actually expands. So because of the increased ocean heat content and temperature, we're seeing sea level rise driven by warming. We're seeing retreat of sea ice. This is particularly important in the Arctic, but we're seeing for sea ice events along New England and the maritime Canadian coasts. Will also increase the amount of evaporation of water. So you'll see more water vapor, but also more precipitation. And I'll get in a minute in detail. The other thing we see on land that's important for coastal communities is as the planet warms, seeing increased melting of glaciers and ice sheets. So mountainous glaciers, and then so Greenland and the West Antarctic ice sheet are seeing dramatic reductions, and water, because meltwater ends up in the ocean, that also increases the amount of mass in the ocean, so it also contributes to sea level rise. So you have sea level rising both because of a warmer ocean and also because of melt of ice on land. The precipitation story, I'll expect to see global precipitation increasing, and there's evidence that it already is. Patterns of rainfall are not uniformly increase. What we're likely to see is regions that are relatively damp will get wetter. Places that are relatively dry will probably get drier. So for example, on this trend map for the U.S., use drying in the southwest that extends into Mexico and Mesoamerica versus the upper tier of the country, the Midwest and the Northeast, that are seeing increased rainfall events, and we expect those patterns to increase in time with further climate change. The other is increase in weather extremes. Often weather patterns, if you look at them over long periods of time, to have a bell curve where you have most of the time period is spent around the middle average conditions. You have for example, here for warming, you have a period of events of very hot temperatures or events of very cold temperatures. At warming, that whole distribution is expected to shift. So for warming, what we'd see is many fewer of the very cold events, cold weather events, but a dramatic increase in what are considered now to be weather extremes. And even periods where you'd have events that have never been seen, so record-breaking. So the sort of orangish red would perhaps the increase in frequency of 90-degree Fahrenheit days. So you might see a factor of 5 or even 10 increase in those, and you might see events well over 100 in record-breaking events hadn't been seen before, depending on where you are. In addition, we're already seeing that, particularly in the Northeast. We're seeing an increase in the intense precipitation events, and this has been looked at by a number of researchers. Not only is the rainfall going up, but it's occurring in more intense bursts, which has important impacts for onshore, on-land, and inland flooding. In the bottom panel, you actually see that borne out, that we're seeing an increase in flooding events in parts of the Northeast and also the Midwest associated with these heavy precipitation events. Researchers here, Carolyn Umenhofer, has been analyzing the long trends in precipitation for the Northeast. So the upper left is showing that pattern of increase in annual average precipitation, and I've marked some of the relatively wet years with anomalously large precipitation that Carolyn has been analyzing, and the patterns of those increased rainfall are shown in the upper right, with a band of increased precipitation stretching from the Midwest up through the Northeast into the Canadian Maritimes. The pattern of increased precipitation is associated with temperatures in the stream region that's shown in the bottom panel. So we're seeing a correspondence between elevated precipitation and warming, and until that might be a dynamical or causal link where increased temperatures in the shore and Gulf Stream region are leading to more water evaporation into the atmosphere and fueling precipitation on land, particularly associated with northeasters that come up the coast and sucking water, so their moisture is the shore, relatively near shore ocean. Temperature can be affecting is hurricanes. So tropical storms, or in the Atlantic called hurricanes, are fueled by ocean heat. The energy that the storms derive, they come to the tropics, have a very thick layer of warm water, and as they move up the north coast, depending upon the surface temperature, that can dramatically affect the strength and intensity of the storm on landfall. They also have the temperature, ocean temperature is also important in other regions as well. One of that's been observed is over time, the ability to track hurricanes has improved with improved forecasting capability and observational capability, and that's shown in the upper panel that for different forecast time periods, the error in the location of the storm has gone down with time, but we have not seen a comparable decline in the error rate for storm intensity. So we can foretell where the storm's going to be, but nearly as well strong the storm is, landfall, and this has important implications for emergency preparedness decisions. One factor in the inability to predict intensity well or improve that forecasting is the ability to track near-shore ocean temperatures and contents that can either continue to fuel a storm or actually to dampen a storm if it goes over relatively cool water. I'm showing here in the upper left a plan that's being put together by consortiums, oceanographic institutions on the East Coast to put a set of buoys, glides, and airborne dropped floats specifically designed to do hurricane forecasting and long-run observations, I should say, and in the long run improve hurricane forecasting In the bottom right, I'm showing results from last summer, where the results from a glider that was released offshore, right offshore of Lowell, southeast New England, where it could actually track right before the arrival of the hurricane the thickness of the warm water on the continental shelf. And this observing system will hopefully be moving forward and will eventually become a standard operational product to improve storm forecasting. There's a debate still in the scientific literature about the impacts of climate change on hurricanes. You will see substantial increases in ocean heat content of the ocean on climate change, so you might expect that hurricanes will increase in both intensity and frequency with time, but there are some confounding factors, in particular associated with changes in patterns. The record on the upper panel does suggest that the amount of power or energy in tropical cyclones in the North Atlantic, that's the red band, does track fairly closely to the sea surface temperature in the North Atlantic. That would suggest that over time, we must expect to see an increase in the most damaging storms. And several of the forecast models all suggest an increase in storms over time in the bottom panel, where current conditions from INCEP, that's the Atmospheric Reanalysis Project, so that's an observational based project in the far left, and model simulations show both an increase in the number of hurricanes and also an increase in frequency of major storms. That would be category 4 and 5, the most damaging storms. I'll shift gears a minute, and I'll come back to a little bit more on hurricanes, but I want to talk briefly about sea level rise, because there's a strong synergy between sea level rise and hurricanes and other storm events. I'm showing here, I happen to live in Lowell, so I'm just showing here the decade record going back to the 1930s. We see increasing sea level its whole. Now, the common pattern seen around much of the country, the local sea level is going to be a combination of global effects associated with ocean warming and melting of glacier and ice sheets, but also have a variety of other local factors, change in ocean circulation that can change the sea surface height, so subsidence or uplift on the land. So we often talk about global patterns of sea level rise and more relative sea level rise, which factors in all of those local effects. Global sea level rise, we have a long record going back, proxy records going for thousands of years. Starting in the late 1800s, we have enough tide gauges to be able to put together reconstructions of the global trends. And what we see from that is about the late to middle 19th century and continuing throughout the 20th century, we've seen an increase across the globe. That's corroborated by recent satellite data that can measure the elevation of the sea surface quite accurately. Moving time into the future, where sea level, the amount of sea level rise depends both on which of those emission scenarios we're on, whether it's a high emission scenario with a lot of warming, relatively low emission scenario, but also on uncertainties associated with melting of Greenland and the Antarctic ice sheet. Rent suggests that those ice are melting and that melting could be accelerating, and helps to explain this large range, anywhere from about a very low end of about a foot by the end of the 21st century to like 6.5 feet. Most people right now, in our understanding, would probably be more comfortable with something in the mid to high end of this range, and that the foot band is thought to be relatively unrealistic. So globally, we're talking about 1 to 2 meters of sea level rise. Are additional local amplifying effects. So, for example, here along the northeast, because of strong ocean current offshore associated with the Gulf Stream, sea level right along the coastline is actually relatively depressed. And under a warming climate, we expect that the stream circulation might actually slow down, and that could contribute another of centimeters to local or regional sea level rise. So we might see a amplification sea level along the east coast from Cape Hatteras up to the Canadian Maritimes. So what the sea level rise? What are some of the effects? Well, even without storms, we have tidal cycles, and showing for a particular location, the daily tidal cycle along the East Coast, we get 2 high tides. We get 2 tides a day, and the magnitude of those tides vary over the month cycle, where you get peak spring tides associated with the full moon and the new moon, and then because of changes in the Earth's orbit, we get king tides. Annually, we're going to have substantial, minor and moderate flooding. There are communities along the East Coast that are already, just because of tidal cycle, seeing tidal inundation at current sea level. At current sea levels, expected to see because of sea level, that the tidal inundation is going to be exacerbated by level rise. And I'm just showing some recent Union Concerned Scientists report where by tide gauge data looking at present day tidal inundation in the land panel, and increases in those events by roughly a factor of 3 to a factor of 10 as we move forward because of sea level rise. Now, it also exacerbates storm surge. So stack to drive water onto the coast, both because they're low pressure systems, and low pressure system, you'll see an elevation of sea level, and also because of winds that tend to push the water onto the shore. So you can get substantial coastal inundation because of storm surge. This is just showing a reconstruction for various storms that have hit New York City over the last 60 years or so. The different components. So the gray is the tidal level. So the damage that a storm does depends a lot on whether it comes in on a high tide or a low tide. The light blue is an estimate of the storm surge driven by low pressure in the atmosphere and winds that pile water up along the shore. And the dark blue is showing the contribution to sea level rise. So as sea level has been rising over time, it contributes a growing proportion of the storm surge. Even if the storm is the same size, because of the level, you see more substantial damage. And for example, the last slide on here is Sandy, where Sandy actually crossed an important threshold, which was the flooding of the subway system. So even if storms stay the same magnitude, because of sea level rise, we'll see an increase in coastal inundation. One of the things that we're concerned about, and I work a lot with a fellow here at Woods Hole named Jeff Doney, is we have a relatively short record for tropical cyclones. Few events each year to really document the typical frequency of storms into observational problems, particularly as you move back in time. So in here is a long-term reconstruction of the number of storms. We think that over the last couple of decades, there may be an increase in the intensity of storms, but it's not clear that the pattern you see with relatively fewer storms in the 1800s and early 20th century whether that's a true reflection of what was going on, or was the fact that we didn't have nearly as good of observational capabilities, particularly in the open ocean. Further back, all you rely on until recently has been historical records, people's diaries, town records, things like that. One of the Jeff has been involved in reconstructing the occurrence of Paleo-Hurricanes using geological methods. And along much of the East Coast, a common geomorphology along the coast is to have a barrier beach right along the coast and marsh or lagoon behind that barrier beach. Storm event, the storm transport sand from that beach into the barrier marsh or into the lagoon, and by drilling cores, such as the one shown on the bottom, you can document the sand layers that are indicative of a storm event. This is indicative of the local intensity, and we heat these using radiocarbon and actually usable proxies in this way. We construct a much longer record of the actual frequency and intensity of tropical hurricanes. This showing the flooding for different historical storms. So this is Jeff has worked with folks using historical observations and also these paleo techniques to document sea level inundation surge along the coastline, and put that data along with estimates of atmospheric winds into, in this case, the SLOSH model. This is a storm surge inundation model built by NOAA. And here I'm showing the peak inundation for an event in the 1600s, which just documented from geological record, and then historical storms that are quite well known in this region. This is showing the Narragansett Bay and Buzzards Bay here in Rhode Island and Southeast Mass. And Buzzards Bay in particular is one of our research sites because it's a natural funnel that tends to enhance the low storm surge. If the storm comes up where the center of the storm east of Buzzards Bay, the cyclonic circulation in the atmosphere, you have winds that are pushing water up to the east of the center of the storm, and dramatic amplifications at the head of Buzzards Bay. This is showing one of these storm surge inundation models. This is 1635 hurricane construction, where you see the storm move on the East Coast, colored wind vectors and low pressure center, and then you have storm surge along the line. And these types of these models, such as SLOSH, we're growing in capability. And there's a growing body of validation data to document their ability to cast storm surge events. About some of these SLOSH models, they can be run for a standard set of storm intensities. In this case, on the right-hand panel, are categories 1, 2, 3, and 4 storms are shown from green to red. I'm actually showing in the upper panel Wareham, Mass, which is the head of Buzzards Bay. So that was the region. This is a blow-up of the region I was showing previously. This is the northern end of Buzzards Bay, a region that's particularly sensitive because of the coastal geometry. And comparison against the FEMA flood insurance maps. And you'll particularly, if you look on the left-hand map, you'll see an orange band that's state high 25. There's a small amount in the FEMA map that goes north of 25. In each model, you see substantial regions where if we were to be hit by a hurricane category 3 or 4, we could see substantial inundations of a much larger region that's currently covered in the FEMA maps. And one of the issues is that we're finding is that the FEMA map is a probability of a certain storm, the 1% storm. You know, frequently would you get the ranging storm that occurs with a 1% frequency? But if we haven't properly reconstructed hurricane frequencies because of poor operational records that don't go back far enough, we may be underestimating the potential damage from storms because we're too weak of a 1%. The chance of the intensity of a storm that has a 1% probability here might be underestimated because we haven't properly accounted for some of these larger storms that have been in the historic period. I've also some other maps, and a lot of these are drawn from the National Estuaries Program for Buzzards Bay, who's a partner with us on the MacArthur grant, where they've done a lot of work documenting at a regional scale how, for example, on the left, the changes in the FEMA maps, but they've also used extensive LIDAR data that's been collected by the state to really compare the inundation patterns and topography that's being used in FEMA versus what they're seeing in the LIDAR data. And what's interesting is there are mismatches, and these are likely errors in databases, GIS data that's being fed into the FEMA maps. So the recent update, there are probably still regions which should be in the floodplain, which are not being included in the red panel. That's the red regions, or that the LIDAR data suggests should be in the floodplain maps, but are not currently. The thing is, moving forward, as sea level rises, you would expect flood zones, the A zone, for example, to extend inland because of rising sea level. Basically, your baseline flood elevation to increase as sea level is rising. And shown in the right-hand panel, a reconstruction for 1, 2, and 3, 1, 2, 4 foot elevation rise in its bay. Now, as I mentioned, 6.5 feet by the end of the century is not out of the question. And see is a substantial incursion, particularly for the in different regions north of, in this case, the town of Wareham, associated with sea level rise, where the plain would actually be expanding with time. I just want to very briefly end about issues beyond condition. There are issues associated with erosion that USGS has done over an extended period of time on a coastal vulnerability, which is looking at geomorphology. So basically, what is the rock type or the soil type on shoreline? Use it to estimate and look at historical shoreline erosion and accretion rates. Coastal slope, basically, how much run-up would there be for an inundation event? The sea level rise, it varies locally because of uplift and subsidence, tidal range, and height. And here is, on the left is, for example, the New Jersey shore region and part of Long Island considered much more vulnerable. A large-scale pattern is associated with changes in geomorphology, to much more sandy soil in New Jersey, and also due to coastal slope, basin regions. We have a growing database for historical shoreline change. This is just shown one region of Cape Cod. Information on the retreat over time, the different colored lines associated with shoreline over different years, going back into the 1800s. And here you see a substantial retreat of the shoreline associated with changes in soil transport and erosion. Trying to model shoreline change under sea level rise. USGS group has been those all the factors that went into their coastal vulnerability index and different shoreline, add in different sea level rise projections and come up with a probable estimate of the retreat on the coastline. So the left-hand panel is showing the probability of shoreline erosion greater than a meter a year. So places that are red, such along New Jersey, just south of New York, or in the Chesapeake, are expected to have very high likelihood of a greater than a meter a year, versus, for example, in Maine, because of the rocky coastline, we expect to see shoreline erosion. One of the that I like about this particular approach versus other approaches is not only do they come up with a probability of shoreline erosion, but they also come up with an uncertainty estimate. How good do you think that, given the current constraints, how well do they think that they know that that estimate of erosion? So, for example, in Maine, because of the rocky shoreline, we think that estimate is quite good. The uncertainty estimate on the right-hand panel is dark red. Also for Chesapeake Bay and parts of New York, in places you have varying estimates of uncertainty that can be considerably lower. So this is very useful for thinking about not only how much do we think it's going to be, but how well do we think we know that answer. That's the end of my presentation. I just want to wrap up for a moment. We've shown the observations and projections for ocean warming. That warming is linked not only to changes in the local environment that might be important, for example, for power plants, marine fisheries, anybody who's using the ocean water where there's a strong sensitivity to temperature, but warming is also related to, for example, the strength of hurricanes, scale ocean warming patterns associated with increases in precipitation in the Northeast, as sea level rise and coastal flooding. So I'll stop there, and I think we're going to take questions through the question and answer, box.
Scott, thank you so much. This is Tom back in Boston. Maybe I'll take the liberty of starting the question and answer. It looked like you were showing at one point that actually in central north, did you actually say that the sea level would be reducing over time?
No.
Did I misinterpret the stuff that you were showing?
Let me pull the plot up. So what you see is right now, so in the top panel, this is an estimate of the surface height. And there's a bulge in the sea surface height offshore associated with the Gulf Stream and along the coastline. That's what the long-term patterns that we see. What we expect to see is that is relaxed. So the bulge offshore won't be as high. The dip along the coastline won't be as low. And that's the bottom panel where you'd see a change. So relative to, we currently live with low sea level rises than we expect if the ocean were not moving. And if the stream slows down, so we'll actually go up more along the coastline than we would expect based on global averages. Tom, does the question?
That clarifies that.
I hear you fine.
The other question I had was, in the face of this, since the project has to do with adaptation, what's your recommendation about how regions should be adapting for what you are forecasting with these models? Are we just sitting here and sort of a lot of trouble, or is it because of the hazard maps or the vulnerability maps that that it just helps us do better policy on that end, or?
Yeah. So, actually, I really recommend taking a look at the Adaptation chapter for the climate assessment. Tony Natos, who's over at BU at the Party School for Long-Term Change, actually was one of the leaders of that chapter. The way I look at how science informs adaptation, for where you have a long time frame, you're making decisions that have long time frame consequences. So, building buildings along the coastline is a good example, or siting of transportation or power lines, plants. The science can provide a much better baseline of risk that because of climate change is probably higher and might affect whether you build the project or what you put in. So there's science informing the risk. There's also a lot of very intelligent design, planning, and engineering solutions that can have multiple benefits, can be put in place to minimize risk from climate change, but also minimize risk from other factors. So, it can be as simple as, the state of Maine, when they're replacing culverts on roads, increasing the diameter of the culvert to try they can't limit the rainfall, but perhaps they can limit the overwash of the road because the culvert's too small when you have increased frequency of rainfall.
So if I'm interpreting right, what I'm hearing you say is that hopefully what it's doing is it's informing this adaptation as opposed to providing a solution. It's really how we then formulate the strategy for adaptation.
Yeah, I don't see that my role for my community is to come up with solutions, but it's to put out the challenges of where we need to come up with solutions, that here are what the problems are, here are what the challenges are. If you tell me that I actually am cleverer than I think and I should be coming up with solutions, please let me know. So.
And the response makes sense, which is it's really guiding what branch of strategy to be taking with certain tools in the toolbox.
One thing that I'm learning though is the way we've done science and communicated in the past has been very one way. I come to my ideas, I do my research, I write my paper, I give a seminar. That's an old-fashioned model. Science really needs to be, scientists need to be engaged with stakeholders, and that can be, governments, that can be business leaders, that can be plant departments, engineers, and really have a two-way dialogue, because it's just science feeding into decisions. How to context for the kind of decisions and challenges helps us design better science that can answer the questions that need to be answered. We can start asking the questions that need to be answered rather than us sort of stumbling along and hoping we're doing the right work. So I really, I'm excited about the project I'm working out with the McCarthy funding, because we're engaging stakeholders and trying to find out what their information needs are, what context in which they're making decisions, which is often more nuanced than a scientist. Scientists think of things often as very black and white. We came up with this data, why don't you make these changes? Well, then you talk to stakeholders and you find out how what a more complicated landscape that they're working in.
And with other fields that I've seen, for example, in the public health area.
Yes.
So that's definitely consistent. We have one write-in question. That's all we really have time for that I want to ask you. And the question is range in estimates do you think it's useful to share with municipalities? The questioner says, I've heard lots of smaller communities just ask for a number about climate change to plan for, and as long as they can't point to a number, it's hard for them to move forward. How do you answer this?
Yeah, I think this is one of the biggest challenges. You know, can't come up with a number both because there's uncertainty in science, the climate science, but also there's a lot of uncertainty in human behavior. The range of future climate driven by emission scenarios is as large or larger than our uncertainty. Start talking about risk and you are for many things like events like storms, you are talking about a change in risk frequency. You know, how often would you expect a damaging storm to occur? How often would you expect a heat wave to occur? And that you know, we're already doing a lot of work to address issue of storm damage, and even for sea level inundation, you know, sea level rise and inundation, most damaging events are either these high tide events or the storms. And there, I would say, well, we give you an exact number, but we can say that the frequency of those events are going to increase, and try to find solutions that are beneficial without climate change, that your risk to damaging storm events will be beneficial. So I wish I could say here's the number, but it's that way, and people are very comfortable. You know, a lot of ways. You know, you talk to business leaders, people are very comfortable with making risk estimates on things like insurance. This gets factored into, you know, a lot of civil engineering design, and I think that's some of the best way that we can come in is, you know, is factoring this into those sort of risk analysis.
Great. I'm going to go ahead and conclude the webinar, and thank you again very much for being the inaugural speaker for the webinar series for the SAGE project. I really appreciate this. This is a terrific setup for the information that's to come in subsequent webinars. So thank you so much for. And I want to know that the next webinar will be on January 23rd, 2015 at the same time, 1 p.m. Eastern Standard Time, again on a Friday. And our speaker is going to be Julie Wormser, who's the Executive Director of the Boston Harbor Association, who will speak on the report that's come out preparing for the rising tide. And it's really outstanding foundation, Scott, that you provide of the inputs and the modeling that's done to provide information for these types of operations, and send out an announcement of that shortly. So, Scott, thanks again so much for making the time to do this.
No problem. Thanks.
Webinar. Thank you very much for attending.